Yeah, thanks so much everyone for coming. It's pretty tough competition. So my name is Jonas Bostrom. During the day, I work at AstraZeneca. I've been there for 20 years almost. I work as a drug designer. All of the time, I try to start up a EdTech company called EduChem VR, where we try to make chemistry a really, really cool school subject. So I'll bring you back in time, teleport you to 1984. I was 10. My mom bought not one, but two Commodore 64s. The reason why she bought two was because I was hogging one of those. It was a really good time learning basic and coding stuff, and then sharing games with the other kids on the schoolyard. It's kind of an early Pirate Bay. And then if we go further back in time to 67, we see that, and compare with today, we see that a lot have changed. So we see that cost has changed 10,000 times. We got an increase in speed 10,000 times. Memory is much better, and size is much smaller. So if we put this into perspective, if we said this is a car instead, if we would see the same progress, this nice German Audi here would have cost €3. It would fit 50,000 people. It would run 1 million kilometers per hour and would fit into this shoebox here. So a lot of happened with computers. Well, what about chemistry then? So I'm a chemist, trained chemist. When I say that, people think this is me. So I have a white lab coat, this glass things, and then there's some colorful liquids and it's bubbling and so on. But that's not me. So this is me at work. So I use computers to solve chemical problems. We do a lot of things, and there are more persons than me looking like this. So why digital chemistry or computational chemistry? Well, it's the same reason for everything else that is being automated nowadays. It's faster, cheaper, and sometimes it's also better. So I'm a computational chemist. So I work in pharma, Big Pharma, and then we call it computer-aided drug design. So what we do then is to try to find patterns and predict stuff. For example, we use machine learning and AI to design better drugs. And what people sometimes forget is that we also use 3D information quite a lot. So we often work according to this key and lock process. So the key, that's the drug that we want to design, and then the lock, that's the protein then. So you see there on the right, we got try to illustrate, so the reddish thing, that's the protein pocket, and then we try to fill that pocket as much as possible, and that's the easy way to explain how you get a more potent molecule, a better drug. So it's a bit like weather forecasting. When I was planning my trip, I thought it was going to be 8 degrees this morning at 8 o'clock. I thought that would be a bit chilly. When I checked the temperature, it was 8 degrees. So weather prediction has been a lot better since when I was young. So it is getting better and better. And the reason for this is, of course, more compute power. Also better algorithm, but we got a lot more compute power. We got that in pharma as well. So that's actually, so that's the design part also, but then we need to make the molecules also. If we go back in time again to the beginning of 1900, the picture on the left there, that's how a lab looked like. And then the lab notebook was the manual thing on the right-hand side, and that's Marie Curie's notebook, and it's actually still radioactive, so you can imagine it's not very safe. If we go forward in time, then we got fume hoods. That's safer, so you can do your chemistry within a fume hood, and then you can start to take notes. Go to 1990s, then we get the electronics and machines. We can do all these cool things, and we can store our lab notebooks electronically. So this is what I think the future will look like. When I tell my real chemist friends, the ones who do the actual chemistry, they just laugh at me. But this is what I think it will look like. So you have your chemical reagents, so that's like Lego. So you have a building blocks, and then you put them together, so that's synthesis, and then you need to clean it up, so that's purification, and then you screen them in the target proteins. And then obviously in this hype area of AI, you have an AI supervising these things. So my friends at work, they laugh at me when I show this, but then I take comfort in Bill Gates. So just take 10 seconds to read it. So if you go back 10 years, for example, I mean, the iPhone didn't exist. So people often overestimate what you can do in 1 year and underestimate what can happen in 10 years. So as I think you start to understand, which you probably knew before and also, is that molecules are three-dimensional objects. The compound on the left there, that's aspirin. If you have some pain, you can take that. And on the right-hand side, you got a famous DNA double helix. And visualizing these and interacting with these is something that the drug designer does on a daily basis. And you can use information and so on. So another thing is size. Molecules are like really, really small. So one typical atom-atom distance is 1.5 angstrom, and that's 10 to the power of minus 19. So what we can do is to make or to see the unseen. We can model things. We can slow down time, and we can predict and learn and so on. Go back in time again. So this is Watson and Crick. They solved the DNA famous helix. And you can imagine how long time it would take to build the DNA helix there. And this is what's happening still. So I have a little bit of an animation here. So this is a molecule. You can spin it, and you got rotatable bonds. So the molecule can assume different conformations. And then you got water molecules coming in. And then you have the protein. We can switch on the surface, and you can see how the drug molecule binds very nicely to its target protein. Switch on there, we can make the surface transparent, and then we can show what kind of interactions, hydrogen bond interactions, for example. So you notice the strange coloring there. So that's obviously yesterday's stereo, so that's anaglyphic 3D stereo, so that's me and my friend Anders in my office. To see stereo, that's obviously really good. If you use red and blue glasses, you can see it, but then it's obviously not perfect. So obviously the future is VR then. So I'll tell you a little bit about our VR journey. So this is Magnus. Magnus had been my summer worker for 5 or 6 years. Extremely efficient guy. In the beginning it was great because then he just did everything I asked him, but then I got kids and then I had to stay at home during the summer because Swedish vacations are 5-6 weeks, as everyone knows, and then kindergarten is closed and need to stay at home. And then I gave him a long list, do this, and then after a week he got a phone call. Well, I'm finished, what should I do now? So both good and bad. So he came to me before Christmas 2014, and he said that he wanted to do his master thesis, and he wanted to do something or use something which called Oculus Rift. I had no idea what Oculus Rift was, but I wanted to try these Microsoft Kinect stuff because I thought that was pretty cool. So I told him, well, if you can do that and hook it up with the Kinect, perfect. Let's do it. After a few weeks or a month or so, then he had built everything from scratch. So we had our own first VR for drug designer. We called it Molecular Rift. And if you go back, so we have this Kinect and the tracker there. And this wasn't ideal if you wanted to do fine interactions. So we hooked on a leap motion instead. And so this is me working. So you see your hand there. You can rotate. If I lift my left hand, there's a menu, and then you can switch on and off things. You can fly around. So this is starting to look okay, I think. This was a couple of years back. You can switch on the ligand, and then you can fly around. So we published it, put the code on GitHub. We got amazing response. People said, well, you're in pharma, you're supposed to be bad guys. So we got good response just because putting it on GitHub, and then people took it, made it available for HTC Vive, for example. And then we got a lot of attention. So this is a pretty interesting story. So that's me and the king of Sweden on the left-hand side there. to make a interesting story, which is quite long. But if you try to show someone VR, it takes a few minutes. I had 3 minutes to show him. So he started out. So he put on the goggles, and then he started to doing like this. And the Queen said, "I'm here." I was like, "What?" So, did she say that? And she did. So how do you react to that? And then I had the opportunity to meet the Crown Princess couple and show them that they had some good comments about we lacked the haptic stuff and so on. So I thought maybe that was it. So because I mean you would imagine AstraZeneca, I mean it's a big company, got a lot of money. We got crap computers, so this stuff didn't work on the computers. We need to integrate stuff. It's not good enough for the experts like myself. It's a bit of an investment, and then that's probably the end of the story then. And then on top of that, Magnus, he moved to Stockholm. He wanted to make money. I mean, if you want to make money, then you go to finance. But then we kept contact, and we realized you can do these things on the mobile phone. Thanks to Unity, because we use Unity, you can basically just push build for whatever platform. It's obviously not that simple. And everyone has an iPhone or a smartphone nowadays, more actually than have a toilet, which is pretty depressing. So how do we apply it then? If you go back to Gates again, it says it's amazing how little the typical classroom has changed over the years. And that's very true, I think. So I teach now and then at the Gothenburg University. When I studied in the late 90s, there were so many people in the classroom. Nowadays, it's not that many. And chemistry is seen as a non-attractive school subject. People think it's abstract, dull, boring, and so on. So we thought we could make that fun. And then you ask, why chemistry? I mean, chemistry, that is everything. So you got like, if you want to have an electronic car, you got lithium-ion batteries in your mobile phone, the screens, cleaning water, antibiotics. If you want to go to the Oktoberfest, which I think should be renamed to the Septemberfest, you can have some beer. And actually 16% of the Sweden's export comes from the chemistry industry. So we started this company called EduChem VR. Why VR then? This is an XR meeting. I'm totally into VR because I think you get the wow effect much more in VR than in AR and the other things. So I think it increases engagement and motivation. In a survey, they saw that 80% of the students were interested in science, but only a third liked those science classes. And then technology is becoming better. Probably not the only one showing this slide, but it's getting better, approaching mainstream, easy to use, some people say. And then I think everyone can agree on that you learn really good by doing stuff. And if you put a person in a place, then it's more likely for them to remember it. And there's evidence that people prove this is the case also. So it's great for understanding abstract concepts like chemistry. We can slow down time, we can see reactions and molecules binding and so on. And then it can also be much more efficient than using physical models. If you have everything prepared, just push of a button and then you got your VR. And the most important stuff, it's really fun to code. And if you reach my age also, when you have kids and so on, then you want to give something back also. So we thought, all you need is a cardboard and a smartphone. So we set out, we made 3 apps quite quickly explaining the carbon structure, the macromolecules, DNA and proteins and so on, and stereochemistry. Our apps were downloaded in many places. It's fun to check. You see in exotic countries like Taiwan and Bangladesh, some people were calling us social entrepreneurs, which was great, I think. And then we realized, so you don't only need the phone and the Google glasses or cardboard. most people like to have something in their hand also, so we added the capability of having a Bluetooth controller. But then, I mean, we're a business, so we should make money. So I checked, so before school started last year, I saw a steady increase in the number of downloads of the apps. And then like 20, 50, 70, 100 a day. And I thought, okay, so let's see if people want to pay for this. So I just swapped on $1 to pay for it. 0 downloads. Kind of depressing. And then I switched it off, and we added ads, and then it was steady. So people didn't mind having the ads, but they didn't want to pay $1, which is depressing. But I think that's the life we live in, and it's probably not good enough either. I mean, if people don't want to pay $1, then it's not good. And then cardboard quality is perhaps not what impresses people. If you want to come in, then yeah. So I thought we need better quality. So I went to another really nice VR conference in London. And then I saw that you could go halfway to the Oculus Rift. You can use the HTC Gear VR, I mean, Samsung Gear VR. But then we realized not that many people have a Gear VR. So, and then we got in contact with a really nice dedicated team from Umeå University. It was a perfect match, I think, because they have teachers, pedagogues, and chemistry professors really interested in this. So we hooked up with them. And then the teacher wanted to do it the old school way. So he wanted to show stuff on the cardboard or monitor. So we went to do web VR instead. So it's kind of poor man's multiplayer version, but that was pretty nice to do it in a web-based, because then people don't have to download the apps, so you just send them a link. So that's it. So we kind of went back to the simple Google Cardboards, because people don't want to pay a lot, especially in schools, for equipment. So we used this A-frame, which was awesome, I think, to work with. And before summer, we finished the first part of this. I'm not really allowed to show this because they have a manuscript which is submitted and should be published any day now. But so they want to use and prove that the VR is good for spatial thinking. I think they have evidence for it also. So from the survey, we see that people think, so it gets an average score of 5 when asked if they think it's a valuable thing. What's interesting also from the free text is that people think that they see real molecules. It's obviously not real molecules, it's models, but it's cool that they think that. And then you could also see a clear correlation between people having problems with the spatial thinking, doing other tests, they have the same problems with VR. And we hope to be able to show that if you train with VR, then you will improve this. So we're just about to start the next phase of this collaboration. So that's university. We want to go to K-12 as well. So my son, he's 13. So he came home before summer and said, we're doing chemistry, we're studying water. And then I said, awesome. What's the difference between solid and solution? And then he said, well, water molecules are closer in solid, in ice, than in solution. I said, no, that's not correct. I mean, oxygen distance is 3 angstrom roughly. So they are not closer. And then he showed me a piece of paper and some nasty drawing or something. I mean, you couldn't understand anything. So I thought, we'll do this in VR instead. At the same time, we had been in contact with Microsoft, and they wanted an app for their Windows Store. So I pitched this idea. So I had exactly my son's, what he was supposed to do and learn. So I took that, and then we made an app which we call Water VR. It's just released. I think we need to improve it a little bit, but it's quite nice, I think. And then you start to understand things, seeing it in 3D and experience it in VR. Problem then is that you need these mixed reality goggles, which are like $500 and so on. So then we're back with the issue of schools paying a lot of money. So we're doing a web VR version of it. It's underway. So I just want to finish off this talk by this slide here. So I think it's great for motivation and engagement VR. So we've been out for science centers and outreach events. I want you to look at this little guy here, Dylan. He's, I don't know, 10 years ago, 10 years or something. He got so much energy. I mean, he was jumping all around. I mean, it was difficult just to talk to him. And then I asked him, try this. I said, no. And then try this. And then he took on the cardboards, and then he was looking for 10 or 15 minutes, just watching like this. And then he went to wave, and then he gave me that note, 10 out of 10. I was like, wow, this is good. So that's what I wanted to talk about today. If you want to be in contact, that's the contact details. So thanks a lot.
Can I have my mic? Oh. So Jonas, that was great. Thank you so much. Does anyone have any questions? I certainly have a question. I was just at a massive CPHL biopharma conference in Madrid. And it's funny that you say that your colleagues laugh at you. It seems so obvious that pharma should be adopting VR. I mean, really, sort of end-to-end through drug development life cycle. Why do you think that is? What is blocking it?
No, I think it's just a mindset thing. I think it will happen. It will just take a few years. So it's kind of frustrating to be in this time now, but it will happen within a few years. But it's mindset and a big company. That's a lot of people who needs to be in the decision making and so on. So, but I'm sure it will happen. We see it in process chemistry. I went to one of the other talks there, so they have it for more AR for explaining things, teaching and knowledge transfer. So it is happening, but it's way too slow, I think.
Slow. All right. Any other questions? All right. Well, thank you so much.